Writing Automated Tests. In his 1972 essay, the humble programmer Edgar W. Kester, said that program testing can be a very effective way to show the presence of bugs, but it is hopelessly inadequate for showing their absence. That doesn't mean we shouldn't try to test as much as we can. Correctness in our program is the extent to which our code does what we intend it to do. Rust is designed with a high degree of concern about the correctness of programs, but correctness is complex and not easy to prove. Rust's type system shoulders a huge part of this burden, but the type system cannot catch every kind of incorrectness, such as Rust includes support for writing automated software tests within the language. As an example, say we write a function call add_2 that adds 2 to whatever number is passed to it. This function signature accepts an integer as a parameter and returns an integer as a result. When we implement and compile that function, Rust does all the type checking and borrow checking that you've learned so far to ensure that. For instance, we aren't passing a string value or an invalid reference to this function. But Rust can't check that this function will do precisely what we intend, which is return the parameter plus 2 rather than say the parameter plus 10 or the parameter minus 50. That's where tests come in. We can write tests that assert, for example, that when we pass 3 to the add_2 function, the return value is 5. We can run these tests whenever we make changes to our code to make sure that any existing correct behavior has not changed. Testing is a complex skill, although we can't cover every detail about how to write good tests in one chapter. We'll discuss the mechanics of Rust testing faculties. We'll talk about the annotations and macro available to you when writing your tests, the default behavior and options provided for running your tests, and how to organize tests into unit tests and integration tests. How to write tests. Tests are Rust functions that verify that the non-test code is functioning in the expected manner. The body of the test functions typically perform 3 actions. 1. Set up any needed data or state. 2. Run the code you want to test. 3. Assert the results are what you expect. Let's look at these features. Rust provides specifically for writing tests that take these actions, which include the test attributes, a few macros, and the should_panic attribute. The anatomy of a test function. At its simplest, a test in Rust is a function that annotated with the test attribute. Attributes are metadata about pieces of Rust code. One example is the derive attribute we used with structs in Chapter 5. To change a function into a test function, add hashtag close bracket test close bracket on the line before fn function. When you run your test with the cargo test command, Rust builds a test runner binary that runs the function annotated with the test attribute and reports on whether each test function passed or fails. When we make a new library project with Cargo, a test module with a test function in it is automatically generated for us. This module helps you start writing your tests so that you don't have to look up the exact structure of syntax of test functions every time you start a new project. You can add as many additional test functions as many test modules as you want. We'll explore some aspects of how test works by experimenting with the template test generated for us without actually testing any code. Then we'll write some real world tests that call some code that we've written and assert that its behavior is correct. Let's create a new library called Adder. The contents of the source library RS file in your Adder library should look like listing 11-1. Listing 11-1, the test module and function generated automatically by Cargo New. For now, let's ignore the top two lines and focus on the function to see how it works. Note that the hashtag test annotation before the function line, this attribute indicates this is a test function, so the test runner knows to treat this function as a test. We could also have a non-test function in the test module to help set up common scenarios or perform common operations. So we need to indicate which functions are tests by using the hashtag test attribute. The function body uses the assert underscore EQ exclamation mark macro to assert that 2 plus 2 equals 4. This assertion serves as an example of the format for a typical test. Let's run to see that this test passes. The cargo test command runs all tests in our project shown in listing 11-2. Listing 11-2, the output from running the automatically generated test. Cargo compiled and ran the test. After the compiling finished and runtime line is the line running one test. The next line shows the name of the generated test function called it underscore works at the result of running that test. Okay. The overall summary of running the test appears next. The text result colon OK means that all the tests passed. And the portion that reads 1 passed, 0 failed totals the number of tests that passed or failed. Because we don't have any tests we've marked as ignored, the summary shows 0 ignored. We also haven't filtered the test being run. So the end of the summary shows 0 filtered out. We'll talk about ignoring and filtering out tests in the next section, controlling how tests are run. The 0 measured statistic is for benchmark tests that measure performance. Benchmark tests are, as of this writing, only available in nightly Rust. See the documentation about benchmark tests to learn more. The next part of test output which starts with doc-tests adder, is for the result of any documentation tests. We don't have any documentation tests yet, but Rust can compile any code examples that appear in our API documentation. This feature helps us keep our docs and our code in sync. We'll discuss how to write documentation tests in the documentation comments as tests section of chapter 14. For now, we'll ignore the doc-test score output. Let's change the name of our test to see how that changes the test output. Change the it underscore works function to a different name, such as exploration, like so. Then run cargo test again. The output now shows exploration instead of it underscore works. Running one test, test, exploration OK, test result OK. Let's add another test, but this time we'll make a test that fails. Test fail when something in the test function panics. Each test is run in a new thread, and when the main thread sees that a test thread has died, the test is marked as failed. We talked about the simplest way to cause a panic in Chapter 9, which is to call the panic macro. Enter the new test, another, so your source library RS file looks like listing 11-3. Listing 11-3, adding a second test that will fail because we call the panic macro. Run the test again using cargo test. The output should look like listing 11-4, which shows that our exploration test and another failed. Listing 11-4 test results when one test passes and one test fails. Instead of OK, the line tests another shows failed. Two new sections appear between individual results and the summary. The first section displays the detailed reason for each failure. In this case, another failed because it panicked at make this test fail, which happened on line 10 in the source library RS file. The next section lists the names of all the failing tests, which is useful when there are lots of tests and lots of detail failing test output. We can use this name of a failing test to run just that test or more easily debug it. We'll talk more about ways to run tests in the controlling how tests are run section. The summary line displays at the end. Overall, our test result is failed. We had one test pass and one test fail. Now that you've seen what the test results look like in different scenarios, let's look at some macros other than panic that are useful in tests. Checking results with Assert macro. The Assert macro provided by the standard library is useful when you want to ensure some condition in the test evaluates to true. We'll give the assert exclamation macro an argument that evaluates to a boolean. If the value is true, assert exclamation mark does nothing and the test passes. If the value is false, the assert exclamation mark macro calls the panic exclamation mark macro, which causes the test to fail. Using the assert exclamation mark macro helps us check that our code is functioning in the way we intend. In Chapter 5, listing 5-15, we used a rectangle struct and a can underscore hold method, which are repeated here in listing 11-5. Let's put this code in the source library's RS file and write some tests for it using the assert exclamation mark macro. Listing 11-5 using the rectangle struct and its can underscore hold method from Chapter 5. The can underscore hold method returns a boolean, which means it's a perfect use case for the assert exclamation mark macro. In listing 11-6, We write a test that exercises the can underscore hold method by creating a rectangle instance that has a width of 8 and a height of 7 and asserting that it can hold another rectangle instance that has a width of 5 and a height of 1. Listing 11-6, a test for can underscore hold that checks whether a large rectangle can indeed hold a smaller rectangle. Note that we've added a new line inside the test module. Use super : star semicolon. The test module is a regular module that follows the usual visibility rules we covered in Chapter 7 in the paths for referring to an item in the module tree section. Because the test module is an inner module, we need to bring the code under the test in the outer module to the scope of the inner module. We use a globe here, so anything we define in the outer module is available to this tests module. We've named our test larger underscore can underscore hold underscore smaller, and we've created two rectangle instances that we need. Then we call the assert exclamation mark macro and pass it the result of calling larger dot can underscore hold and smaller, reference smaller. This expression is supposed to return true, so our test should pass. Let's find out. It does pass. Let's add another test, this time asserting that a smaller rectangle cannot hold a larger rectangle. Because the correct result of the can underscore hold function in this case is false, we need to negate that result before we pass it to the assert exclamation mark macro. As a result, our test will pass if can underscore holds returns false. Two tests that pass. Now let's see what happens when our test results when we introduce a bug into our code. Let's change the implementation of the can underscore hold method by replacing the greater than sign with a less than sign when it compares the widths. Running the tests now produced the following error. Our test caught the bug. Because the larger dot width is 8 and the smaller dot width is 5, the comparisons of the widths in can underscore hold now returns false. 8 is not less than 5. Testing equality with the assert underscore eq exclamation mark and assert underscore ne exclamation mark macros. A common way to test functionality is to compare the result of the code under test to the value you expect the code to return to make sure they are equal. You could do this using the assert exclamation mark macro and passing it an expression using the equal operator. However, this is such a common test that the standard library prefers a pair of macros assert underscore eq exclamation mark and assert underscore ne exclamation mark to perform this test more conveniently. These macros compare two arguments for equal and equality respectively. They'll also print the two values if the expression fails, which makes it easier to see why the test failed. Conversely, the assert exclamation mark macro only indicates that it got a false value for the equal expression, but not the values that led to the false value. In listing 11-7, we write a function named add underscore 2 that adds up 2 to the parameter and returns the result. Then we test this function using the assert underscore equal exclamation mark macro. Listing 11-7, testing a function add underscore 2 using the assert underscore eq exclamation mark macro. Let's check that it passes. The first argument we gave to the assert underscore eq exclamation mark macro 4 is equal to the result of calling add underscore 2 2. The line for the test is test it underscore adds underscore 2 OK, and the OK indicates that our test passed. Let's introduce a bug into the code to see what it looks like when the test that uses assert underscore eq fails. Change the implementation of the add underscore 2 function, instead add 3. Run the test again. Our test caught the bug. The it underscore adds underscore 2 test failed, displaying the message assertion failed, left equal right, and showing that left was 4 and right was 5. This message is useful and helps us start debugging. It means that left argument to assert underscore eq exclamation mark was 4, but the right argument, where we had 2 underscore 2 was 5. Note that in some languages and test frameworks, the parameters to the functions that assert 2 values are equal are called expected and actual, and the order in which we specify the arguments matters. However, in Rust, they're called left and right, and the other in which we specify the value we expect and the value the code under the test produces doesn't matter. We could write the assertion in this test as assert underscore eq exclamation mark add underscore 2 to 4, which would result in a failure message that displays assertion failed, colon left equal right, colon, and the left was 5 and right was 4. The assert underscore ne exclamation mark macro will pass if 2 values we give it are not equal and fail if they are equal. The macro is most useful for cases when we're not sure what a value will be, but we know that the value definitely won't be if our code is functioning as we intended. For example, if we're testing a function that is guaranteed to change its input in some way, but the way in which the input is changed depends on the day of the week that we run our tests, the best thing to assert might be that the output of the function is not equal to the input. Under the surface, the assert underscore eq exclamation mark and the assert underscore ne exclamation mark macros use the operators equals and exclamation mark equals respectively. When the assertions fail, the macros print their arguments using debug formatting, which means the values being compared must implement the partial EQ and debug traits. All of the primitive types and most of the standard library types implement these traits. For structs and enumerations that you define, you'll need to implement partial EQ to assert the values of those types are equal To assert that those values of those types are equal or not equal, you'll need to implement debug to print the values when the assertion fails, because both traits are derivable traits as mentioned in listing 5-12 in chapter 5. This is usually as straightforward as adding the hashtag square brackets derive colon partial EQ comma debug colon square brackets annotation to your struct or enumeration definition. See Appendix C, derivable traits, for more details about these and other derivable traits. Adding custom failure messages. You can also add a custom message to be printed with the failure message as optional arguments to the assert exclamation mark, assert underscore EQ exclamation mark, and assert underscore NE exclamation mark macros. Any arguments specified after the one required argument to assert exclamation mark or the two required arguments to the assert underscore EQ exclamation mark and the assert underscore NE exclamation mark are passed along to the format exclamation mark macro discussed in chapter 8 in the concentrate with the constantation with the positive operator or the format exclamation mark macro section. So you can pass a format string that contains curly brackets, placeholders, and values to go inside those placeholders. Custom messages are useful to document what an assertion means. When a test fails, you have a better idea of what the problem is with the code. For example, let's say we have a function that greets people by name and we want to test that the name we passed into the function appears in the output. The requirements for this program haven't been agreed upon yet. We're pretty sure that the hello text at the beginning of the greeting will change. We decided we don't want to have to update all the tests when the requirements change, so instead of checking for exact equality to the value returned from the greeting function, we'll just pass assert that the output contains the text of the input parameter. Let's introduce a bug into this code by changing greeting to not include name to see what the test feature looks like. Running this test produces the following. This result just indicates the assertion failed and which line the assertion is on. A more useful failure message in this case would print the value we got from the greeting function. Let's change the test function, giving it a custom failure message made from a format string with a placeholder filled in with the actual value we got from the greeting function. Now when we run the test, we'll get more information, a more informative error message. We can see the value we actually got in the test output, which would help us debug what happened instead of what we are expecting to happen. Checking for panics with should underscore panic. In addition to checking that our code returns the correct values we expect, it's also important to check that our code handles error conditions we expect. For example, consider the guess type that we created in chapter 9, listing 9-10. Other code that uses guess depends on the guarantee that guess instances will contain only values between 1 and 100. We can write a test that ensures that attempting to create a guess instance with a value outside this range panics. We do this by adding another attribute, should underscore panic, to our test function. This attribute makes a test pass if the code inside the function panics. The test will fail if the code inside the function doesn't panic. Listing 11-8 shows a test that checks the error conditions of guess : new happen when we expect them to. Listing 11-8 testing that a condition will cause a panic. We place the hashtag close bracket should underscore panic close bracket attribute after the hashtag close bracket square bracket test square bracket attribute and test the function it applies to. Let's look at the result when this test passes. Looks good. Now let's introduce a bug into our code by removing the condition that the new function will panic if the value is greater than 100. When we run the test in listing 11-8, it will fail. We don't get a very helpful message in this case, but we look at the test function, we see that it's annotated with hashtag close bracket should underscore panic close bracket square bracket, I'm sorry. The failure we got means that the code in the test function did not cause a panic. The tests that use should underscore panic can be precise because they only indiciate that the code that the code has caused some panic. A should underscore panic test would pass even if the test panics for a different reason from the one we were expecting to happen. To make should underscore panic test more precise, we can add an optional expected parameter to the should underscore panic attribute. The test harnesses will make sure that the failure message contains the provided text. For example, consider the modified code for guess in listing 11-9 where the new function panics with different messages depending upon whether the value is too small or too large. Listing 11-9 testing that condition will cause a panic with a particular panic message. This test will pass because the value we put in the should underscore panic attribute expected parameter is a substring of the message that the guess : new function panics with. We could have specified the entire panic message that we expected, which in this case would be guess value must be less than or equal to 100 got 200. What you chose to specify in the expect parameter for should underscore panic depends on how much of the panic message is unique or dynamic and how precise you want your test to be. In this case, a substring of the panic message is enough to ensure that the code in the test function executes the else if value greater than 100 case. To see what happens when you should underscore panic test with an when a should underscore panic test with an expected message fails, let's again introduce a bug into our code by swapping the bodies of the if value less than 1 and the else if greater than 100 blocks. This time when we run the test, should underscore panic test will fail. The failure message indicates that the test did indeed panic as we expected, but the panic message did not include the expected string guess value must be less than or equal to 100. The panic message that we did get in this case was guess value must be greater than or equal to 1 got 200. Now we can start figuring out where our bug is. Using result T E in tests. So far, we've written tests that panic when they fail. We can also write tests that use result TE. Here's the test from listing 11-1, rewritten to use result TE and return an error instead of panicking. The it underscore works function now has a return type result less than colon, comma, string greater than in the body of the function. Rather than calling the assert underscore EQ exclamation mark macro, we return an OK when the test passes and an error with a string inside when the test fails. Writing tests so that they return a result T and E enables you to use the question mark operator in the body of tests, which can be a convenient way to write tests that should fail even if any operation within them returns an error variant. You can't use the hashtag square bracket should underscore panic square bracket notation on tests that use result TE. Instead, you should return an error value directly when the test should fail. Now that you know several ways to write tests, let's look at what's happening when we run our tests and explore the different options we can use with cargo test. Controlling how tests are run. Just as cargo run compiles your code and then runs the resulting binary, cargo test compiles your code in test mode and runs the resulting test binary. You can specify command line options to change the default behavior of cargo test. For example, the default behavior of the binary produced by cargo test is to run all tests in parallel and capture output generated during test runs, preventing the output from being displayed and making it easier to read the output related to test results. Some command line options go to cargo test and some go to the resulting test binary. To separate these two types of arguments, you list the arguments that go to cargo test followed by the separator and then one that goes to the test binary. Running cargo test dash dash helps display the options you can use with cargo test, and running cargo test dash 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 help displays the option you can use after the separator dash dash. Running tests in parallel or consecutively. When you run multiple tests, by default they run in parallel using threads. This means tests will be finished running faster so that you can get feedback quicker on whether or not your code is working. Because the tests are running at the same time, make sure your tests don't depend on each other or on any shared state, including a shared environment, such as a current working directory or variant variables. For example, say each of your tests runs some code that creates a file on a disk named test-output text and writes some data to that file. Then each test reads the data in that file and asserts that the file contains a particular value, which is different in each test. Because the tests run at the same time, one test might overwrite the file being between when another test writes and reads the file. The second test will then fail, not because the code is incorrect, but because the tests have interfered with each other while running in parallel. One solution is to make sure that each test writes to a different file. Another solution is to run the tests one at a time. If you don't want to run the tests in parallel, or if you want to run more fine-grained control over the number of threads used, you can send the --test threads flag and the number of threads you want to use to the test binary. Take a look at the following command example. Take a look at the following example. We set the number of test threads to 1, telling the program not to use any parallelism. Running the tests using one thread will take longer than running them in parallel, but the tests won't interfere with each other if they share state, showing function output. By default, if a test passes, Rust test library captures anything printed to standard output. For example, if we call print line exclamation mark in a test and the test passes, we won't see the print line exclamation point explanation mark output in the terminal. We'll see only the line that indicates the test passed. If the test fails, we see whatever the printed to standard output with the rest of the failure message. As an example, listing 11-10 has a silly function that prints the value of its perimeter and returns 10, as well as a test that passes and a test that fails. Listing 11-10 tests for a function that calls print line exclamation mark. When we run these tests with cargo test, we'll see the following output. Note that nowhere in this output do we see I got the value for, which is the which is what is printed when the test that passes runs. That output has been captured. The output from the test that failed, I got the value of 8, appears in the section of the test summary output, which also shows the cause of the test failure. If we want to see printed values for passing tests as well, we can disable the output capture behavior by using the --no capture flag. When we run tests in listing 11-10 again in the --no capture flag, we see the following output. Note that the output for the tests and the test results are interleaved. The reason is that the tests are running in parallel, as we talked about in the previous section. Try using the --test threads equal 1 option and the --no capture flag and see what the output looks like then. Running a subset of tests by name. Sometimes running a full test suite can take a long time. If you're working on code in a particular area, you might want to run only the tests pertaining to that code. You can choose which tests to run by passing cargo test the name or names of the tests you want to run as an argument. To demonstrate how to run a subset of tests, we create 3 tests for our add_2 function as shown in listing 11-11 and choose which ones to run. Listing 11-11, 3 tests with 3 different names. If we run tests without passing any arguments, as we saw earlier, all the tests will run in parallel. Running signal tests, We can pass the name of any function in cargo test to run only that test. Only the test with the name 1_100 ran. The other two tests didn't match that name. The test output lets us know we had more tests than what the command ran by displaying two filtered out at the end of the summary line. We can't specify the names of multiple tests in this way. Only the first value given to cargo test will be used, but there is a way to run multiple tests. Filtering to run multiple tests. We can specify part of a test name, and any test whose name matches that value will be run. For example, because two of our test names contained add, we can run those two by running cargo test add. This command ran all tests and in the name and filtered out the test name 1_100. Also note that the module in which a test appears becomes part of the test name. So we can run all the tests in a module by filtering on the module's name, ignoring some tests unless specifically requested. Sometimes a few specific tests can be very time consuming to execute, so you might want to exclude them during most runs of cargo test. Rather than listing as arguments all tests you do want to run, you can instead annotate the time-consuming tests using the ignore attribute to exclude them as shown here. After hashtag test, we add the hashtag ignore line to the test we want to exclude. Now we run our tests. It works, runs, but it_works runs, but expensive_test doesn't. The expensive_test function is listed as ignored. If we want to run the ignored test, we can use cargo test -- ignored. By controlling which tests to run, you can make your cargo test results be faster. When you're at a point where it makes sense to check the results of the ignored tests and you have time to wait for the results, you can run the cargo test -- ignored instead. Test organization. As mentioned at the start of the chapter, testing is a complex discipline and different people use different terminology and organization. The Rust community thinks about tests in terms of two main categories: unit tests and integration tests. Unit tests are small and more focused, testing one module in isolation at a time. It can test private interfaces. Integration tests are entirely external to your library and use your code in the same way any other external code would, using only public interface and potentially exercising multiple modules per test. Writing both kinds of tests are important to ensure that pieces of your library are doing what you expect them to, separately and together. Unit tests. The purpose of unit tests is to test each unit of code in isolation from the rest of the code to quickly pinpoint where code is and isn't working as expected. You'll put the unit tests in the source directory in each file and with the code that they're testing. The convention is to create module named tests in each file to contain the test functions and to annotate the module with the CFG test. The test module and hashtag CFG test. The hashtag CFG test annotation on the test module tells Rust to compile and to run the test code only when you run cargo test and when you run cargo build. This saves compile time when you only want to build the library and save space in the resulting compiled artifact because the tests are not included. You'll see that because integration tests go in a different directory, they don't need the hashtag CFG test annotation. However, because unit tests go in the same files as the code, you'll use the hashtag CFG test to specify that they shouldn't be included in the compile result. Recall that when we generated the new adder project in the first section of this chapter, Cargo generated this code for us. This code is automatically generated test module. This code is the automatically generated test module. The attribute CFG stands for configuration and tells Rust that the following items should only be included given a certain configuration option. In this case, the configuration option is test, which is provided by Rust for compiling and running tests by using the CFG attribute. Cargo compiles our test code only if we actively run the tests with cargo test. This includes any helper functions that might be within this module, in addition to the functions annotated with the hashtag test. Testing private functions. There's debate within the testing community about whether or not private functions should be tested directly, and other languages make it difficult or impossible to test private functions. Regardless of which testing ideology you adhere to, Rust's privacy rules do allow you to test private functions. Consider the code in listing 11-12 with the private function internal underscore adder. Listing 11-12, testing a private function. Note that the internal underscore adder function is not marked as public, but because tests are just run code and because tests are just Rust code and the tests module is just another module, you can bring internal underscore adder into the test scope and call it. If you don't think private functions should be tested, there's nothing in Rust that will compel you to do so. Integration tests. In Rust, integration tests are entirely external to your library. They use your library in the same way any other code would, which means they can only call functions that are part of your library's public API. Their purpose is to test whether many parts of your library work together correctly. Units of code that work correctly on their own could have problems when integrated, so test coverage of the integrated code is important as well. To create integration tests, you first need to test directory. You need a test directory. The tests directory. We create a test directory at the top level of our project directory next to SRC. Cargo knows how to look for integration tests files in its directory. We can then make as many test files as we want to in this directory, and Cargo will compile each of the files as an individual crate. Let's create an integration test. With the code listing 11-12 still in the SRC libraries RS file, make a test directory. Create a new file named tests/integration underscore test.rs and enter the code in listing 11-13. Listing 11-13, an integration test of a function in the address crate. We've added user address at the top of the code, which we didn't need in the unit tests. The reason is that each file in the test directory is a separate crate, so we need to bring our library into each test crate scope. We don't need to annotate any of the code in tests / integration underscore test.rs with hashtag closing brackets CFG test closing brackets. Cargo treats the test directory specifically and compiles files in this directory only when we are in cargo test. Run cargo test now. The three sections of output include the unit test, integration test, and the doc tests. The first section for the unit tests is the same as we've been seeing, one line for each unit test, one named internal that we added in listing 11-12, and then a summary line for the unit tests. The integration test section starts with the line running target /debug /deps /integration underscore test dash and a bunch of numbers. The hash at the end of your output will be different. Next, there is a line next to each test function in the integration test and a summary line for the results of the integration test just before the docs-tests address section starts. Similarly to how adding more unit test functions add more result lines to the unit test section, adding more test functions to the integration test file adds more result lines to the integration test files section. Each integration test file has its own section, so if we add more files to the test directory, there will be more integration test sections. We can still run a particular integration test function by specifying the test function's name as an argument to cargo test. To run all the tests in a particular integration test file, we use the --test argument of cargo test followed by the name of the file. This command runs only the tests in the tests / integration underscore test.rs file. Submodules in integration tests. As you add more integration tests, you might want to make more than one file in the test directory to help organize them. For example, you can group the test functions by the functionality they're testing. As mentioned earlier, each file in the test directory is compiled as its own separate crate. Treating each integration test files as its own crate is useful to create separate scopes that are more like the way end users will be using your crate. However, this means files in the test directory don't share the same behavior as files in source do. As you learned in Chapter 7 regarding how to separate code into modules and files, the different behavior of files in the test directory is most noticeable when you have a set of helper functions that would be useful in multiple integration test files. And you try to follow the steps in the separating modules into different files section of Chapter 7 to extract them into a common module. For example, if we create test /common.rs and place the function name setup in it, we can add some code to setup that we want to call from multiple test functions in multiple test files. When we run the tests again, we'll see a new section in the test output for the common.rs file. Even though this file doesn't contain any functions, nor did we call the setup function from anywhere. Having common appear in the test results with running 0 tests displayed for it is not what we wanted. We just wanted to share some code with other integrating test files. To avoid having common appear in the test output, instead of creating tests /commons.rs, we'll create tests /common /mod.rs. This is an alternative naming convention that Rust also understands. Naming the file in this way, Rust won't will tells Rust not to treat the common module as an integration test file. When we move the setup function code into test/common/mod.rs and delete the test/common.rs file, the section in the test output will no longer appear. Files and subdirectories of the test directory don't get compiled as separate crates or have sections in the test output. After we've created test/common/mod.rs, we can use it from any of the integration test files as a module. Here's an example of calling the setup function from the it_adds_to test in test/integration_test.rs. Note that the mod common declaration is the same as the module declaration we demonstrated in listing 7-21. Then in the test function we call the common : setup function. Integration tests for binary crates. If your project is a binary crate that only contains src/main.rs file and doesn't have a source library file, we can't create integration tests in the test directory and bring functions defined in the source main.rs file into scope with a use statement. Only library crates exposed functions that other crates can use. Binary crates are meant to be run on their own. This is one of the reasons Rust projects that provide a binary have a straightforward source/main.rs file that calls logic that lives in the source/library.rs file. Using that structure, integration tests can test the library crate with use to make an important functionality available. If the important functionality works, the small amount of code in the source/main.rs file will work as well, and that small amount of code doesn't need to be tested. Summary: Rust testing feature provides a way to specify how code should function to ensure it continues to work as expected, even as you make changes. Unit tests exercise different parts of a library separately and can test private implementation details. Integration tests check that many parts of the library work together correctly, and they use the library's public API to test the code in the same way external code will use it. Even though Rust type system and ownership rules help prevent some kinds of bugs, tests are still important to reduce logic bugs having to do with how our code is expected to behave. Let's combine the knowledge you've learned in this chapter and in previous chapters to work on a project. Okay, that concludes chapter 11. Next we will do chapter 12.